Angel's introduction on parsing, I'm introducing this metric for evaluating the document level semantic graph, because as we know, UMR is an interconnected sentence graph. So instead of like instead of separated individual sentence graph that is collected together in a document, the UMR is actually the sentence graphs are interconnected with temporal and coreference dependencies. So so we need such kind of evaluation matrix to quantify the quality of a UMR graph in two ways. So the first is like we need to measure the inter-annotator agreement to assess the annotation consistency among the annotators. So for example, during the production of the UMR dataset, the UMR 1.0 and 2.0 data, we typically for one document we have 2 or more annotators to do the same annotation for the same document. And so obviously they will have some disagreement on some of the annotation, and we need to quantify like how far are they from each other. And the other end of this evaluation matrix is to evaluate the UMR parsing accuracy. So if we have an automatic a pipeline method or it's an end-to-end method which generates a graph, we have a gold graph, have a gold standard graph. We have to compare like how and quantify how well this parser works. So take this for example. Now we have two annotations. Whether so let's say this is the correct answer, the correct graph, and that is either without generated by a parser, or it is annotated by another annotator. So we can see there's some difference. So for example, the biggest difference here in the secret sentence, like so the sentence is we missed the sentence here. So but it is not that important. So the sentence is like this is. Just give me a minute. So the original sentence for the two graphs, basically they are the same annotation for same sentence. So sentence is activists allege that the prisoners were likely being mistreated yesterday. Their allegation went unnoticed by the public. So the biggest difference between these two graphs is whether there should be an annotation of the verb go, because there's a sentence called went unnoticed by the public. So actually this is a correct, because go here is like a light verb, so it shouldn't be annotated. But however, like this sentence, it has this kind of extra note, but this does not. So we need to quantify like the score. Like how is this graph diverge from this graph? And we need to give it a score for this. So of course there are some other difference between, because for example there's this kind of plural this attribute annotation for activist, while this graph does not have this kind of thing. And also this aspect is different, because like this mistreat it should be annotated as activity, but instead it is annotated as performance here. So we see that there's a multiple difference, but how can we give a score? And so the general approach is because the UMR it consists of a number of sentence level graph, and also with other kind of dependencies. Like there's some inter-sentence relations, like from this S1A to this S2N, then after, which is a temporal relation. So this means this one is like this sentence goes across boundary of the sentence, so the sentence graph, and also this coreference relation also goes beyond the sentence boundaries. So our goal is to evaluate the 4 components separately, and also we provide a general score to quantify the document level annotation. And we can note that the UMR graph is actually represented as multiple triples. So each of these relations can be represented as a triple. And if we aggregate them together, they become this graph-like structure. But we resort to calculate the score based on these triples. So the most crucial thing is to align the nodes between these 2 graphs. So this node is a concept or is a kind of an attribute. So in order to compare the UMR graph, we need to align the nodes among the graphs. But the biggest problem, the biggest issue here is that the 2 UMR graphs may not align 100% if they have different node names, or they even have different number of nodes. For example, this node is extra compared to this graph, and also they have different number of nodes, where some nodes exist here but not here. So the alignment is not a trivial thing. It's not a trivial problem. So we cannot assume that there are nodes in the graph aligned to the word and text, because there are a lot of abstract concepts. For example, the sentence is actually activist alleged that the prisoner could be mistreated yesterday. So we see that lots of words do not exist in UMR annotation. Instead, there are some UMR nodes that do not exist in the original sentence. For example, this person, because we are only seeing that these are prisoners. But in UMR, according to guidelines, we need to annotate them as this kind of named entity. So this named entity, this person concept, never exists in the original sentence. So we cannot assume that the nodes in the graph align to the word and text. Let alone there are a lot of abstract concepts which will never exist in the original sentence text. So such alignment could be used to such alignment. There are some alignments as you may use as you're using the UMR tool. You can see there are some alignments that align to the original sentence, but in a lot of cases, especially the abstract concept, this alignment do not exist. And but we still need to align the abstract concept between the 2 sentences. So we resort to an algorithm that we proposed last year, which is called anchor and broadcast. So to introduce this algorithm kind of simply, because make it less technical, I will go through the general idea of this algorithm. So we start from the intrinsic node similarity. So for example, we want to align the nodes between these 2 annotations. So suppose they are annotation for the same sentence, some kind of stir fry, and we see that this fry and this stir fry, they have some kind of similarity, and both of them contain fry, and so they have an intrinsic node similarity, which is to quantify the string similarity, which is fry, and also so first we only focus on the concept part instead of the sense ID part. So fry compared to stir fry, it's like 70. It's a 3/8 similarity, And also they have some attribute similarity, which is because to this concept it has 3 attributes, and this one has 2 attributes. And among their attributes, 2 of them they have the shared attributes, which is both of them have this quant attribute and the polarity attribute. But only half of their shared attributes are the same. They have the same polarity attribute, but their quant attribute is different. So the attribute similarity is 50%, and their sense ID is different. So we have a overall similarity for these 2 nodes, which is based on this formula, which means like if they have both the string and some shared attributes, their similarity is calculated as the average of their attribute similarity and their string similarity, which is about 42%. And we calculate the intrinsic node similarity for.
Sorry, you can finish your sentence. Go finish.
Yeah. So this is only the example for one node. So there are like if one graph has 5 nodes, the other graph has 6 nodes, we'll generate a matrix of 5 times 6 matrix, because each node you can calculate the intrinsic similarity to every other node in the other graph. But the problem is sometimes the names is totally different. So for example, in these 2 graphs, each of them have 5 nodes. We only see that read and read share the same string form. And but for other things like it's simply based on strings, we can never know like they are the same thing. So semantically we know that house and home may be similar, but because we are it's this lightweight tool, we don't want to use some things like the vectors. So we don't know that house and homes are aligned. And for he and she, like they have some string similarity, but they are still not aligned because maybe they are semantically similar, but we cannot assume that they refer to the same node. And also, so here there's a thing like I and I. They have the same form, but the thing is like in the original sentence we don't have this word because so this is derived from my. So original thing is like called my, but in UMI annotation we need to convert it to this subjective form. But it does not appear in the original sentence, so we still do not have this confidence to say that they refer to the same concept. But for read, we have confidence to say that they refer to the same concept, because read is we know that it's from reading, and read only appear in the or in the original text for only one time, and so this read and this read we have confidence that they refer to the same concept in the original sentence. So now if we calculate the intrinsic similarity of these 5 nodes to all the 5 nodes in both sentences, we can have this kind of matrix. So read and read is like 90% similarity because they don't have the same sense ID. And this he and she, it has this kind of string similarity, but it's so this is a coincidence because but this coincidence will not affect the final node alignment quality. So this is 67% of similarity, and this I and I have 100% similarity solely based on the string. But we see that the other alignment is all 0 because they don't have the same form, and it's possible that this form is actually like the read should it's possible that he should not be connected to she, but instead connected to home. So all these alignments possible. So we need to fill up these 0 So the way we do this is that we do this kind of broadcasting based on these anchors. So the anchors are the alignments that we have confidence that they are actually aligned. So actually in these two graphs we only have one pair of nodes that we have confidence that they're really aligned, is the read to read, and all the other things are zero. But we can broadcast it. So this broadcast means, so it's based on assumption that the aligned node, if two nodes is aligned, their neighbors are likely to be aligned. So for example, this house and this home, they have the neighbor is read. And for this for this book, it has two neighbors. So it has a parent, it has a parent node which is read, and it has a child node which is I. So if their neighbors have more nodes that they can be aligned, they are more likely to be aligned. And so we use this kind of broadcasting. So it's based on sing rank, so which is a single graph broadcast, and we adopt it to our scenario, which we make it in a bi graph broadcast. So which means so this house, it has an anchor with read, so gradually it will have a higher ability. So this house and this home, they have a higher probability of being linked. So here we can see that. So this broadcast will finally converge to a stable version. So here is home to house. We can see that because home, he, book, and I, they have the same set of neighbors. So their neighbor scores similarity are the same. So home, it has the same probability of being linked to home or she or paper. But for I, it's kind of different because I have a different set of neighbors. So we time this neighbor similarity to their string similarity, and we found and we only pick those local maxima. So for example, if we time this intrinsic similarity to this neighborhood similarity, we can see that he and she and I are the local maxima, and also book to paper. Because book to paper, they have two neighbors, so their similarity is kind of higher because only a book and neighbor have two neighbors. All other nodes have only one neighbor. So now in the second round, so after first round, we start from 1 anchor to 4 anchors, and we do the broadcast again. And still we cannot align home and house, but they are the only left pairs. So we align them. So now we got this anchor, this node alignment for all the 5 nodes. So for details, you can refer to a paper. I'll put the link in the end because I don't want to put too many formulas here. So there's. Oh.
So sorry. So how in the 2 slides ago, how are you accounting for? Sorry, I did one more. Exactly. Attributes that appear in one AMR or one UMR, but not the other. Is that in the attribute similarity score? Or? So I mean, like here, mode imperative appears on the one on the left, but not on the one on the right.
Yeah. So here, so this one is just I'm trying to give it like a more plausible score. So this mode means because mode is not a shared. Share is not a shared attribute. So this one does not have mode. So I just ignore. I just ignore this mode.
Okay.
Or only consider this two.
What if there were a whole bunch of attributes in the left UMR but not the right UMR?
So if there's a whole bunch of attributes here, but no attribute here, so in this case, the attribute is not considered.
Okay.
Because sometimes it may be that the attributes are wrongly allocated. So it just if it's like a multiple to 0, so this one should be 0. This denominator should be 0. and this similarity is also 0. So we only consider the string here.
Okay, so I'm going to mention that it wouldn't be possible to get a super high AnCast score if you have basically a blank UMR or just a rooted UMR, because none of the attributes would be.
This is different because this intrinsic node similarity is only for node alignment. So if one UMR has multiple attributes and the other one don't have any attributes, then in calculating the actual score, it will be different because this one has multiple relations, multiple triples. This one only has like even 0 triples.
Okay.
Yeah.
Okay,
So this is not the final score.
Okay.
This is only for node alignment.
So it only matters for node alignment. Okay.
Yeah.
Thank you.
Yeah. So here I'm introducing how we calculate the final score. So previously in S-match, the S-match simply counts like how many relations, how many triples are the test graph has that overlap with the goal graph. So we propose that we need to consider two factors. So the first is the concept of one, like whether they are mentioning the same set of concepts, and the other thing is the labeled relation of one, like we consider among all the triples, like how many of them are shared. The shared means they have the same concept and the same relation. And because we have this kind of node alignment as similar as to S-match, we can also serve as an alternative to the traditional S-match score. And we will show that based on the node alignment, we can generate a high correlated score to S-match. So the concept of one is also only consider the intrinsic node similarity. So we will not consider the attributes. So this is a concept of one. So it's only it's like a referential score, like a supplementary score to the final to the relation to the relation score. So whether two graphs are about the same content, which means so here the precision and recall, if they have the same number of nodes, the precision and recall are the same. So here like we can see read and house, home, and like each on that line, and we just calculate the average of their intrinsic similarity. So if this UMR have lots of attributes, this is not considered here. It's considered in the next slide. So in the next slide, so this is a label relation F1. This means like we consider all the relations among in the two in the two annotations. So we can see that in total there are only 4 relations for each graph, and for each relation we can find its counterpart, because if two relations because like for the first pair we can say that read is connected to read and no house is aligned to home, and we know that we can say that these two triples are aligned, and because they are aligned, we can calculate the similarity of them. Like here, they have the same relation, and the read and read they have a point line similarity, and home to house they have the 0 similarity in their string form. So this is only like 45% of similarity, and for this one, because they have a different relation label, so they are like 0. So to Shir's question, if we have another attribute here, for example, if we have this kind of a mode, so and this we do not have a mode, and this have mode aspect and wall string, so there will be 3 extra triple here without being here. So this means the recall stays the same. If this is the correct graph, the recall is the same, because for all the 4 triples, it has its counterpart, but the precision is low, because for the extra 3 triples, it does not have a counterpart in the other graph. Yeah. And so we compare this because this is basically a sentence level graph. So we can compare it to other matrix to evaluate parsers. So we see that if we can, because we have a known alignment, we can mock the S-match score, and we have a high Pearson correlation to in all parsers results. And generally, this label relation microwave one is 10 or more % lower than S-match, meaning that it captures more things. It captures more errors than S-match. And we also have a weighted relation, like we assign higher relation to the relation that is closer to the root. And the runtime is only 40% of the S-match. This means this node alignment approach is much more efficient than the S-match approach. And so let's recap these two graphs, because we are proceeding to the other three modules of UMR: the modality, the temporal, and the coreference annotations. So how can we? So after we have this node alignment, so we already know that this don't align. How can we quantify the annotation quality or the parser quality of these relations? This before or after this after or this kind of same entity? How can we quantify the quality of this annotation? Can we just simply count? And the answer is like we cannot simply count this temporal and the coreference relation. And we have some reason later. So the sentence score. So this is the alignment of the nodes. So we can see that go 08 in this graph is left alone because it's an extra node compared to the gold graph. And so now the sentence score the sentence score is 12 out of 7 and 12 out of 6 for record, for precision and record, because here we all the string similarities is the same. Only here is some difference in the student's ID. And yeah, so here the model dependency is built upon the node mapping. So this is the model dependency for the for the reference model for the reference graph, and also this is for the incorrect graph. And because they are not this model dependency is not cross sentence, so we can simply count. We can see that this relation and this relation, the risk relations, is correct because they are mapped from the same pair of aligned nodes, and these two relations are not correct because they are from the different head and tail. So both precision and records are 26 because they have the same number of relation. And how can we quantify temporal and coreference relations? So there's a very tricky and important property in temporal and coreference relation is that there are transitivity among these relations. For example, if we have annotation of A is before B and B is before C, we can deduct that A is before C. So if we have two annotations, one annotation only say A is before B, B is before C, and the other annotation say it's instead it has some redundant annotation, which one have the graph 1 only has 2 annotated relations, but graph 2 has 3 relations, but they are basically the same. So, but simply counting will generate, it will yield wrong, incorrect result. And this is the same for coreference. Like if A is equal to B, B is equal to C, we can deduct that A is equal to C. But if it does not annotate, but the other graph annotates this or generated this result, simply counting will yield an erratic result. So so here we propose that we can have an algorithm to complete these these missing relations and calculate. And then after we complete the transitive relations of the temporal and coreference relations, we can then produce a more reliable evaluation matrix of the temporal and the coreference annotations or parsing result. So this is called transitive closure of temporal and coreference relations. And so the first one is to complete the whole graph, so complete all those transitive relations. So we first convert these relations into this kind of more abstract representation, and we also observe a property is like we can cope with this temporal and the coreference relation in the same manner, because for both of them we are dealing with their transitive properties. So for both of them we can complete them in a similar manner. So we can convert them in the same representation, and we can use a shared composition table of these relations. And note that in UMR we not only do we have after and before, we also have other kind of relations like subset of, and subset is actually works in the same manner as in the overlaps. These two relations in temporal relations, they don't have transitive properties. So this is a converted. So that's so this is a picture example. So this is the original annotation for of the two graphs. So we can see that so S1y is have a relation to S1a. So S1a is after S1y and S2n is after S1a. So these dashed lines are the completed transitive relations. So for example, for S1n, why here is a after relation? It's because S1n is a subset of S1i. So S1y contain S1n, and S1y is before S1a. So we can deduct that S1n is also some event that precede S1a, and so on and so forth. So S1n is precede S12, S2n, and also document creation time, and S1a is before R. And here in the other graph, we have different completion. So S3m is before S4g because it have these two transition, and S3m is also before S4n because S4n is a sub event of S4g. So we can deduct that S3m is also before S4n, and all these relations can be completed with this composition table. So we can use this composition table for automatic inference. So we start from each node to see whether there are any inferred relation that can start from this node, and the details are in the paper. Yeah, and so now we have now the temporal graph is completed. It is transitively complete. So we calculate how many relations are here are how many of them are overlapped among these two graphs, shared over these two graphs, and we adopt a link-based approach, and we'll introduce later. So the covariance scenario, in covariance scenario, also from the two graphs, from these two graphs, so they have relatively much fewer coreference relations among these two graphs. So we can see that there's the same. So the only difference is like the same entity is correctly annotated, but same event is not correctly annotated, because there should be a relation here. So how do we score this transitive closure? It's based on this formula, but this looks very complex, but it's not. It's actually very simple. So basically, let's take the coreference as an example, because this is relatively simple. So we can see that here there are two clusters. This is the same event cluster, the same entity clusters in the goal graph, and this one it has three clusters. So we incorporating the precision, we divided by the total number of nodes, and we for each cluster we calculate how many relations in this cluster is correct. So for the test graph, the first cluster only have one node, so it does not have any relation that is shared with the other graph. And this is same for this cluster. And for the cluster of the two same entity, the relation is correct. So this one is 1 out of 1 relation is correct, and divided by the total number of nodes. So this is 0.5. And for the recall, it has 4 nodes and have 2 clusters. And in the first cluster, it does not the relation does not have any counterpart in the other graph, so it is 0. And in the second cluster, the relation it only has 1 relation, and the relation is correct, so it has the 1 out of 1. It's not correct. It's just like it has this counterpart in the other graph because we have the node alignment. So this is also 0.5. And for the temporal, because the two temporal only have 1 clusters, so we divided by the total number of nodes and how many temporal relations are shared out of the total number of relations, and times the nodes in this cluster. So because it only have 1 clusters, so this 6 is the same as this 6. And so how can we compute a comprehensive UMR score? So the goal of this step is to make sure that the 4 modules are weighted the same, because the first 2 modules, the sentence level graph and the model dependency, their weights are based on the number of nodes. Their weights are based on the number of relations, but for temporal and coreference, because they are transitively closed, their calculation are based on the number of nodes to make sure they are the weights on the same magnitude. So because sentence level graph is based on tree-like structure, so the number of relations in the sentence graph is basically the same magnitude as the number of nodes in the sentence graph. So we adopt the number of relations in sentence graph and the number of relations in modality, that the number of modality relations, but we adopt the number of nodes of the temporal graph with the nodes that are annotated with temporal relations, and the number of nodes that are annotated with coreference relations. So to make sure that all of the 4 weights are with the same magnitude of being n, about ON. And so the final precision is calculated as the weights times the sentence score, and the weights times the modality score, and the weights times the temporal score, and the weights times the coreference score divided by the total sum of weight. So the precision of the graph is 0.64, and the recall is 0.67, and we can calculate the F1 score with these with this precision and recall. And this is a more complex example to illustrate that the difference of the transitive closure performed to coreference and to temporal. So the dashed line are the shared transitive closure to both coreference and temporal relation. So for example, like if 6 is a sub-event of 4, and we can know that 1 is before 6. But however, if 5 is a super event of 3, like for example 3 is like the whole yesterday, but 5 is last week, but 1 is 3 days ago. So we know that 1 is before 3, but 5 still contains 1, because 5 is like the whole last week. So in temporal relation, this dotted line cannot be inferred. But in coreference scenario, this dotted line can be inferred. Because if 1 is equal to 3, then 5, if 5 contains 3, 5 is also a superset of 1. So this example is in the appendix of the paper to illustrate the difference. The difference in computing the transitive relations in temporal scenario and also coreference scenario. So we use this aggregate score to evaluate Gio's parsing result, and we can see that all we have result for all the scores, and we can have an aggregate score, and we can cope with the scenario where some of the modules do not have annotation. For example, in this Chinese parsing, the temporal annotations are not there and are not allocated. So, but it has a 0 weight, so this do not affect the calculation of the final final aggregate score. And so, conclusion is that we propose a new matrix that include a more fine-grained F1 score, and using a very efficient algorithm that has a polynomial runtime compared to the S matrix, which is a non-polynomial runtime. And we also propose an evaluation matrix for document level graph for UMR, including temporal and coreference relation under the same framework. Yeah, thank you.
So, any questions for you?
The slides are going to be shared.
Yes,
Yeah, it'll be
Okay.